Hello, this is Math Kimchi, and in this video, I'll be discussing the Buddhabrot Fractal, which is a cousin of the Mandelbrot set. So, to start, I'll talk about the Mandelbrot set. And I've actually already talked about the Mandelbrot set in another video, but that was like 2 years ago. So, anyways, um, this is what the Mandelbrot set looks like. It's uh, it's a set in a complex plane. So the fact that it's a complex plane means that this axis represents the real axis. So the numbers like 1, 2, 3 and negative pi or something like that. And here we have the imaginary axis. So that's like I, 2i, negative 5i, uh, like the square root of -1. And every point that you are seeing here represents uh, a point, or every pixel that you see here represents a point in the complex plane. So approximately here you would see the origin. So yeah, that'd be just the number 0 or 0 plus 0i. And all the way here is 2, -2. This is 2i, this is -2i, and the for every point on this complex plane, for example, let's choose a point like this. We are running, there's a corresponding sequence, and that sequence starts at 0, 0, though I chose not to do it because it'll get kind of chaotic. And the 0th element of the sequence is going to be 0. The first one is going to be the point, and we usually represent that with the constant c, and then z2 is going to be this point, z3 is this point, z4 is here, and z5 is all the way over here somewhere. And the way we get from one element to the next is by saying z n plus 1 is equal to z of n squared plus c, and that c is that point that we're looking at. And for that sequence, we're trying to see if that sequence ultimately goes unbounded and off to infinity, or unlike these blue and red points, if it just stays finite. And the way we compute that is by saying if any of these points, any of these iterations ever leave the circle with radius 2, then we will know that it's never going to come back, and we can say that it just goes off to infinity. And with points like this, it escapes in one iteration, or the second iteration escapes. With this point, the third iteration is the one that escapes, and anything with this color escapes in 2 or 3, depending on how you phrase it. And the bluer you get, the more iterations it takes, until eventually you get to one of these black points, and this point is what we call in the Mandelbrot set. And the Mandelbrot set is just the set of all the points in the complex plane that does not go off to infinity when we run it through z of n plus 1 is equal to z of n plus c. And you could see that this creates a very beautiful shape, and this resolution is kind of low, so hopefully this one is better. And theoretically, if we had infinite resolution and also infinite iterations to test, if we kept on zooming in, it would it would never get boring, is one way to describe it. And so the perimeter of this the Mandelbrot set is infinite, despite it having a finite area. It's obviously going to be less than the area of the circle of radius 2. And that's the Mandelbrot set, and it's heavily based on that equation, z of n plus 1 is equal to z of n squared plus c. And with that equation, we could do a lot of other things. And one of those other things is called the Buddhabrot set. And this image is actually rotated by 90 degrees. This image is what it would look like if it had the same range as this image here. So you can kind of see the similarities, and instead of moving the Buddhabrot, I'm just gonna show an image where the Mandelbrot set is also shifted. So you can see how a lot of these points kind of coincide, or a lot of these patterns within these shapes. So you could see how there's like this circle-like shape here, and this cardioid is also present in both shapes, and all of the other points on the Mandelbrot set, you could kind of see an equivalent here. And even this this little island here, you could see that over here, and it's like a mini island of the Buddhabrot set, or the Buddhabrot Fractal. And so what actually is this? What does it represent? It represents the probability that for all of these points, for any of these points, that a path of one of these unbounded sequences is going to pass that pixel. So that's kind of like a abstract definition, and the technical definition is more clear. So pretty much what you do is you start with a blank slate, either completely black or completely white. I chose to start out completely dark, so all of these pixels were at 0. Let's pretend it's a grayscale for now. So all of these values were gonna start off at 0, and then we choose a random point inside of the circle of radius 2. So let's say I chose this point. Well, this isn't very interesting because it leaves instantly. So let's choose this point. And in that case, we can start off by ignoring the zeroth and the first iterations. I do that just because I think that just makes more sense. It's not really saying much that a point is going to pass on the first iteration or the zeroth iteration, because the zeroth iteration is going to be 0, 0 no matter what, and the first one is going to be the initial point. And so, with those two exceptions, we are going to find the pixel that corresponds to the second iteration point, and then we're going to increase that by 1. So it's like a density or probability map. And every time this random iteration passes through, each of these pixels are increased slightly. So this point, this probability is increased by 1. This is increased by 1. This is increased by 1. This is increased by 1. Same with all of these, except for when we're in a Mandelbrot set. And for those points, if we recognize that it actually never leaves, then we're not going to plot any of those. And the reason why is because if we do, then it's another fractal called the anti-Buddhabrot fractal, where it's the same concept, except kind of like the inverted starting conditions. But anyways, we, for all of these, are just choosing random points over and over again, and then updating the density map slightly and making it slightly brighter every time. And eventually, some of the points are going to be passed more than other points. And in here, you could see that like the general clump here is getting passed often, and that kind of makes sense because in my mind, if you ever go like near the edge of the radius 2 circle, then it's going to be hard to go back in. So a lot of these bright points are because before something leaves, it kind of stays around before leaving. And then that's why it's not just like a flat map, and there's actually a lot of detail to this. And you could see that this kind of pattern repeats here and here and here, and this big pattern repeats here and here and here and here. And it's just fascinating to look at how all these probabilities kind of repeat. And of course, the resolution is relatively high. It's 4,000 by 4,000, and to make this look less noisy, I'm gonna need even more iterations. Not iterations, but just sample points. And I've already had 1 billion sample points, which is quite a lot. And even still, it's not completely smooth. So that just goes to show how computationally intense this Buddhabrot fractal is. And anyways, before I was talking about simply a grayscale, and I do have an image of that, and it looks like this. and this is done slightly different. And unlike the Mandelbrot, I'm not simply just taking something that is one dimensional and uh, making it look like it's three dimensional. Uh, for an actual RGB Mandelbrot or an RGB Buddhabrot, what you do is you do the process I described earlier for uh, three separate times, and each time you want to choose a different uh, maximum iteration, and then the each different case would correspond to a different color in RGB. So for this image, I chose 5,000 for red, 500 for green, and 50 for blue. And that's why even when they're different, there's still like points that all of them kind of have bright. I think either this or this, they're always the brightest. Once you get to like a certain number of iterations, they're really the bright ones. And yeah, it's kind of resembling the chi points of the Buddha, and you can kind of see why this is called the Buddhabrot Fractal, because especially I think the head looks a lot like Buddha's head, where there's a lot of these things for his like hair, and also the chi points, and his hands are kind of in like the meditation position, and this is the main cardioid is his body. And yeah, it's kind of similar in the Mandelbrot set, but just this looks so much more like Buddha, and yeah, it's just very beautiful to look at and to zoom in and find the different recurring patterns. And uh, this was, as I mentioned earlier, had like the maximum iteration of 5,000, and the number of sample points was 1 billion. So in the worst case, I would have had to test uh, 5 trillion different iterations possible. But obviously, some of them left earlier. So it's not like 5 trillion, but I'd assume it's around at least 1 trillion, just from the fact that this is so big. And yeah, even the ones that do escape, they're not always escaping instantly. So uh, anyways, this was 4,000 by 4,000 pixels. I don't think that actually impacted the performance that much, because the main thing that impacts the performance is just the total number of iterations, which is going to be changed by the maximum iteration, and also the just the number of points to iterate through. And with these settings, I had to use multi-threading, and I ended up with having to spend 2 hours on this. So this was a log, and yeah, it took around 2 hours and 20 minutes. And I think this means I branched out 5 times. So there were 2 to the 5. So I think there were 32 or maybe 63 cores working on this. I think 32 uh like very leaf layers, because I try to make it like a tree, and it didn't actually improve my performance 32 times. I think in the smaller testing cases it was around twice, or somewhere between 2 to 3 in the best case, and sometimes it even made their performance worse. But I made sure that wouldn't happen for this, because that would have been pretty bad. But this was a project that I did in Rust, and it was my first Rust project. And just reflecting on the project, it was pretty fun to implement all of the math while I was learning a new language. And yeah, the ownership stuff, it was pretty interesting. And sometimes it didn't make sense, but I think I mostly understand it now. And yeah, I'm just happy I got to learn an actually fast language as opposed to Python, which I did 2 years ago, or yeah, maybe even 3 years ago, when I made my first video on the Mandelbrot set. And you could see this took around like 20 seconds, even for a 500 by 500 grid. So it would have taken much, much longer for any of these images that I made. And I also had to try to make this brighter, because the very first colored image looked like this. And this image is actually based directly off of this, but I made it brighter, and also I rotated it 90 degrees just to make it look more like Buddha. And for this one, even though all of the actual data in here is the same, it's actually even, there's more data in here than in here, because here I ended up repeating some like colors, even if in here they were different. But in the end, this looks like harder to tell all the bright and dark points, whereas this has a bit better like colors to just tell everything. And yeah, this is gonna be on my GitHub and in the links. But that's pretty much it for the Buddhabrot Fractal. Thanks for watching.